you need a mic?
Actually, we're recording.
But then nothing is streaming, right? I was trying to stream. Nothing is.
No, actually, before it was in private mode. So yesterday we make it public.
Okay. So I tried streaming on Saturday. It was not streaming. Now it is.
Yeah, you can see. Now it is. We made it public.
Okay. Yes, so that yes, so Chrome gives me this. I mean, I was trying.
We have to allow the flash player.
Yeah. So I mean, I was trying to stream on Saturday. So first of all, I had to figure this out, and then Chrome keeps giving me warning that flash player is. This will go on. Hello.
Okay, so our next speaker is Riddhipratim. We'll be talking maybe about that equation also, but about eigenvalue rigidity and connections with first passage percolation.
Thanks, Piyush. Yeah, I thank the organizers. Yeah, so I'd like to thank the organizers for giving me the opportunity to speak and organizing this very nice meeting. Unfortunately, much of which I have been missing. So, for those of you who know me, that you must know that I know literally nothing about random matrices. So what is this talk about? The abstract says something about eigenvalue rigidity. So this talk will be mostly about, I'll tell you a story which connects two quite separate fields of probability. One is random matrix theory and other is the field of last passage percolation. And what is the most remarkable fact about this story is that they are connected at all. So this story is not new. It has been around for about 20 years, but what I'll try to tell you maybe is some recent aspects of this story that are still unfolding. So this formula, this is the probability density. So this is the probability density on the cone. And this will be a very important object connecting these two separate branches of study. So let me start with, so what am I talking about? So there are two different things. So let me make, on one side of the story is some classical random matrix ensembles. I'll describe these models in more detail later. So, I'll tell you a connection for two specific models, one here and one there, but this story is more general, so there are parallel stories for other ensembles as well, but just for concreteness, I'll stick to the following. So consider a matrix of IID So I have an n by n matrix of IID standard complex Gaussian entries, which means that the real part and imaginary part of each of the entries are independent and standard normal random variables with mean 0 and variance half. And we consider the Wishart matrix. Okay, so this is the Wishart matrix, which is a positive definite, so it has n non-negative eigenvalues. And it is a classical fact, so it goes back to, I don't know, maybe Marchenkov and Pastur in late 60s, early 70s. So when people started studying eigenvalues of of random matrices, one of the first models they considered is this Wishart, and the first result, the classical fact. So let me say, so let me consider the eigenvalues of this matrix and order them. Okay. So one of the first things people discovered for this Gaussian matrices is that it is quite easy to write down the joint density of the eigenvalues. You can integrate out the eigenvectors. And it turns out that the joint density of the eigenvalues for that matrix is this quantity for m equal to n and beta equal to 2. Yeah, so m equal to n is nothing special. If I started with x and m by n matrix, then the same density will hold just for two separate values m and n. But beta equal to 2 is crucial, so that corresponds to the unitary invariance of this model. So this is called the Laguerre unitary ensemble. Okay, so these are all very classical facts, 40, 50 years ago. So what more do we know? So it's actually not very hard to see if you can just do some trace computation that the eigenvalues of this matrix W, they scale linearly in n. So to get some suitable limit, you should scale things by n. So if I just denote lambda I tilde to be equal to lambda I by n, and if I look at the empirical measure, so this is the random probability measure which puts mass 1 over n at each point, each scaled eigenvalue lambda I tilde, then this almost surely weakly converges to what is called the Marchenko-Pastur distribution. And let me also write down the density of the Marchenko-Pastur distribution. So it's a distribution with compact support, supported on the closed interval 0 to 4, and the density on that interval is given by this quantity. Okay, so this is all quite classical. And then something that is probably not so classical but still fairly well known is the distribution of largest eigenvalue. So if you look at lambda 1, see this, after scaling by n, I have got a distribution which has support 0 to 4. So the largest eigenvalue, you would believe that it should be somewhere close to 4 times n. And indeed that is the case. So if you subtract this leading order term 4n from the largest eigenvalue and this is not lambda 1, this is lambda n, and scale by some constant times n to the 1/3, this converges to what is known as the GUE Tracy-Widom distribution. It's a well-known distribution in random matrix theory. So it's called the GUE. Okay, so that's the basic facts about Laguerre unitary ensemble. So now coming back to this side of the board, let's say what is last passage percolation. So it's a model. You will see that apparently has no relation a priori to what I have been talking about so far. What is this? So we have the two-dimensional Euclidean lattice, and on each vertex I put a weight. So this is the somewhere here is y. So I have the full two-dimensional lattice, and at each vertex I am putting a random weight. I am putting some weight, and let's say that these yij's, these are iid, exponential random variables with rate 1. Okay, so what is the object of interest here? The object of interest here is the following. So starting from this bottom left corner, I'll consider some path that moves up or right and reaches the vertex nn. So for such a path, let's call this path phi. So this path is phi. Then the length of that path will simply be just the sum of the weights on that path. Okay. And the interesting quantity here is the last passage time, which is you take supremum over all upright paths that start from here and go up to here, and you take supremum of the length. So that is called the last passage. Okay, so why is it called a percolation? One way to think about it is as follows. So you start initially with the whole, just the first quadrant, and at time y11, this vertex 1, 1 becomes occupied, and then each vertex can become occupied after weighting the amount of weight that is assigned to it, but subject to the constraint that for a vertex to become occupied, both its left neighbor and bottom neighbor have to have become occupied. So the clock starts after that. So you can think of it's some way of modeling flow of fluid through a media or something like that. So that's the more standard one is the first passage percolation, where you move as fast as you can, but here it's the other way. So you're looking at the maximum maximum weight path, but it's similar in spirit. Okay, so that's the model of last passage percolation. Now where is the connection? So okay, so maybe before that let me mention some other classically well known fact. So it's known, again this has been known for 40 years almost. So this is that this last passage time from 1, 1 to nn, this also scales linearly with n with constant 4. And yes, yes, and you maximize over all staircase paths.
If you were to assume all of these paths are independent of each other,
Yes, but they are not.
But would you still get 4 or?
No, that will be completely different. So if all these paths were independent, then you can calculate very easily, because each of the paths will have Gaussian fluctuation, and you have.
No, what would be the number be? You know?
So I mean, it's quite easy to calculate. So each path has okay. So each path has weight. So right. So there are about 2 to the n many paths, and each of the paths, the expected. Yeah. So okay. So I can't offhand do the calculation, but the point is that each of the paths has expected length 2n, and it's essentially it's a gamma distribution.
Directionally, what
So
is
you
expected?
so it will be so if it's independent, then probably it should be larger, because you have lots of independent variables, right? So it's very likely that one of those paths will be very large. So there will be 2 to the n independent paths. So you can just this 2 to the n entropy has to be balanced with the tail decay of the gamma variable. So it's in the calculation. I can do it with, give me 30 seconds, but let's not go into that. So it's something that the major difficulty in studying this problem comes from the fact that these paths are highly overlapping. So that creates a very complicated dependent structure. Okay, so the thing started getting interesting when in 99 Johansson proved the same result. So this is 99. So if you subtract 4n from Tn and divide by the same constant times n to the 1/3, you get again the same limiting distribution. Okay, and this is no magic. I mean, there is a magic, but that these two distributions are same is no magic. There actually is a correspondence at finite level. So the remarkable distributional equality that connects these two apparently disparate models is that for any finite n, the distribution of the last passage time from 1, 1 to nn is exactly equal to the distribution of the largest eigenvalue of that Wishart matrix. Okay, so it's really comes out of thin air. So the way it's done is that now there are lots of ways to see it, but the way at least Johansson did it, so he actually wrote down explicitly the joint, the distribution for Tn, where the edge weights were geometric rather than exponential. There you can write it down using some Markov property of the growth process, and then you just take the exponential going to geometric going to exponential limit, and this formula pops up. Okay, so somehow this formula is the one that connects the the last passage percolation and the classical random matrix, classical Laguerre unitary ensemble. By the way, I should mention there is this beta here. So this is for a general beta, it's called the beta ensemble. So if beta equal to 2, it's usually the unitary ensemble. Beta equal to 1 is the orthogonal ensemble. Beta equal to 4, the symplectic ensemble. So these are some of the more interesting values. So there are connections for last passage percolation models with beta equal to 1 and beta equal to 4 beta ensembles as well. But we'll for today's talk we'll just stick to this beta equal to 2 connection. So last passage percolation, what Johansson proves. So what he did, he started with geometric weights. So there is a correspondence. There is something called geometric RSK correspondence. For those of you who have seen this RSK correspondence for uniform permutations, there is a version of that's called geometric RSK correspondence. So using that geometric RSK correspondence, you could write down explicitly the last passage time distribution for geometric weights. And now, geometric, you can take a limit. So if you send the parameter to 1, and you scale appropriately, if your Q is like 1 minus 1 over L and you scale the variables by L, then geometry goes to exponential. So if you take that limit, so that in the literature is known as Meichner to Laguerre limit, if you do that, then you get that the distribution of the density of Tn is the same thing when you integrate lambda 2 up to lambda 1 up to lambda n minus 1 out. Okay, so let me mention it here. I'll maybe come back to it at the very end of the talk if I have time. Okay, so let me keep this question here for a while, and I'll come back to it at the end of the talk. So now what we have seen that there is this random matrix, Wishart random matrix, whose largest eigenvalue has magically the same distribution as the last passage time in the last passage percolation with exponential random variable. So for those of you who are familiar with random matrices, you all know that this Tracy-Widom distribution, this is nothing unique for the Wishart matrix or the Laguerre ensemble. It is believed to be universal. Wishart matrices with non-Gaussian entries, or just Hermitian matrices like Wigner matrices, they also have the largest eigenvalue edge scaling limit is Tracy-Widom distribution, and that is actually now been established with lots of work by this group of Tao and Wu, and also this group of H.T. Yao and his collaborators. They have more or less now saturated this field. And so there is a corresponding story in the last passage percolation picture as well, that the scaling limit of the last passage time should be Tracy-Widom. It is believed not to depend on the specific nature of the model, namely the exponential nature of the distribution. So the last passage time, obviously the constant 4 will change depending on what distribution you put, but it is believed that if you center by whatever the correct constant is, and divide by n to the 1/3 times whatever the correct constant is, you will get to see again this GV Tracy-Widom distribution. But this question, unlike the question of universality in random matrix theory, this question remains wide open. So there are roughly like 3 or 4 different models for which people can show this Tracy-Widom scaling limit for the last passage time, and that too mostly when there is a connection to some other exactly solvable model like some random matrix model. So there is, for exponential there is this connection to LUE, for Brownian last passage percolation, if you know what that means, and otherwise don't worry about it. So there is the exact correspondence to GV, there is correspondence to Meichler line ensemble. So usually there are like 4 or 5 models where there is, you can write down explicitly the density of the last passage time in terms of some orthogonal polynomial ensemble. So depending on your understanding of asymptotics of this orthogonal polynomial ensemble, you can then maybe do some asymptotics and get this result. But there is no general theory of universality like there is for random matrices. Okay, but it's physicists predict, and it's very widely believed that the last passage percolation models also exhibit the same universal behavior. All right, so here also, if you have heavy tail distribution, it is known that you don't have Tracy-Widom. So there is, and not even you don't have Tracy-Widom, this n to the 1/3 scaling itself will change. So so what happens is that there is a work by Nick Ziguras and Parthode, and followed up later last year by Kotoa Borkar, where they sort of give you the exponent, the relation between exponents. So as far as I understand, they don't characterize the limiting distribution, but what they can tell you is that if you have a power law tail, then and it's slow enough. So if it's fast enough, I think it's believed that if power law is more than 6, then it comes back to Tracy-Widom. But if it is between 2 and 6, something like that, then there is a different exponent. So the formula of that exponent is known to some degree, but the limiting distribution, as far as I know, is not characterized. Okay, so the story I've been telling you so far, it's nothing recent. So this much was already known in '99, and in the intervening 20 years, people have people have used a lot of random matrix results in understanding last passage percolation models, in particular this model of exponential last passage percolation, but also other models. So what I'll spend the remaining 20 minutes of the talk telling you is some recent understanding is where it has emerged that not only the top eigenvalue, but understanding the whole profile of eigenvalue distribution in some specific sense can also lead to interesting consequences in the last passage percolation world. Okay, so this brings us to the question of rigidity. So suppose I consider this quantity. So lambda i's are between 0 and 4n roughly, and there are n of those, right? So approximately, so this is all heuristic, there's nothing, I'm not saying anything rigorous. So approximately the density is like 1/4. So if you had a Poisson process on 0 to n with density 1/4, this quantity, how much would it fluctuate by? So if you have a Poisson process of a constant density on an interval of length n, how much it will fluctuate by? It will fluctuate by a lot, right? So you'll get something like, so each entry will have variance of the order n square. So the total variance is n cube, so fluctuation is something like order of n to the 3/2. So this is not true obviously, this is heuristic in Poisson calculation. But what is summation lambda I? Summation lambda is just the trace of the matrix, right? The trace of the matrix is again sum of n IID variables. So their fluctuation is actually of order n to the 1/2. So this is a phenomenon that is often referred to as the theory of point processes as rigidity, meaning that something has fluctuations much smaller than a Poisson-like process, which means that things that are spatially independent. Now, it's actually not very difficult to see why such a thing should be happening. Just looking at the density, this van der Monde term here implies that whenever lambda I minus lambda j is too small, you are paying a lot of, so beta is 2, beta is greater than or equal to 1 in particular. So whenever lambda I minus lambda j is too small, the density is very small. So those parts of the space have very small mass. So there is a repulsion basically between the eigenvalues, and that means because they are constrained to be in this region 0 to 4n, if things cannot get too clustered, it means that they cannot get there cannot be large holes either. So what essentially heuristically this would suggest is, if you look at the ith eigenvalue lambda I and you look at the corresponding quantile of the Marchenko-Pastur distribution, they should be very close. Okay, so this is the phenomenon that is called rigidity. So let me, sorry? A hole means that a region where there is no eigenvalue. If you think of it as a point process, it means that there is no point there. Okay, so what is rigidity? So this is, so let gamma I. So gamma is the ith I over nth quantile of the Marchenko-Pastur distribution. So rigidity phenomenon tells you, so lambda I tilde, remember that is the one that is the thing that converges to Marchenko-Pastur distribution. So phenomenon of rigidity for our purpose will be the phenomenon that lambda I tilde minus gamma I is small. Small in the sense that small compared to if lambda I would have been lambda I would be independent random variable with mean gamma I and appropriate variance. So the distance here would be smaller than that. Okay, so there is another kind of rigidity that is of interest. So that is called the rigidity of linear statistic. Okay, so think about classical central limit theorem. So gamma is something deterministic. So I have sum of n quantities, each of which has mean about 0. So if you are in the classical case where these things are decorrelated, you expect that after centering by 1 over square root n, you get a central limit theorem. But here what happens is that this quantity is tight in itself without any centering. So that's another manifestation of the phenomenon of rigidity. So you have sum of n random quantities. Because things are very rigid, so even after summing, the fluctuations don't add up. You don't need to scale by square root n like you would in the classical central limit theorem setup. So that is rigid, that is called. Okay, so for smooth ellipses F. Okay. So these are kind of things that are, so this thing is, you can think of it as a smoothed out version of the individual eigenvalue rigidities. So this is actually easier to prove. So this is already known by and Gonzatti-Kamlov. Okay, so that is for the central limit theorem, because there is a lot of averaging going on. It turns out that proving rigidity of the individual eigenvalues, sometimes it is a little difficult. So that's very recent result by Bourgade, Yao, Yin. This is maybe from 5 years ago, which shows gamma I. So I will not define precisely what I mean by bulk, but what essentially they show is that if you're if you are neither too close to the left edge of the spectrum or too close to the right edge of the spectrum, then with high probability your lambda I minus gamma I, lambda I tilde minus gamma I is this much. So if you are in the bulk, if you are really in the bulk, then minimum of I and n minus I is still of order n. So this is like 1 over n, the thing in the denominator, and the log n to the log n thing is something that is spurious, that comes from the proof. So you would believe typically, for most of the eigenvalues, lambda I minus gamma is actually of order 1 over n. But this is what is there in the literature. And there is also another kind of rigidity result, which which is to show rigidity at the edge. So, okay, so maybe I'll come back to that later. I don't have that much time, maybe come back to that later if I have time. Okay, so let's leave the rigidity there. So what kind of things we can use this rigidity result for? It turns out that there are a lot of things one can do, but I want to give one specific example, that is of large deviation. So suppose, for example, so now lambda n we have said its typical value is like 4 times n. So large deviation mean asking what happens to this quantity. And in particular, we'll be interested in this quantity. Okay, so let me briefly show you how one can use rigidity result to get very sharp control on this thing. So is it still visible if I write here? Oh, no, maybe do not cross, I should not. Okay, so let me go somewhere, maybe let me erase this. So that's why this formula that I have up on the board since the start becomes useful. So notice that if I change lambda to lambda tilde, the only thing that changes, so I'm putting beta equal to 2. So the constant in the constant z changes, but the only thing, and if m equal to n, then the lambda I powers of lambda I they vanish, because m plus 1 minus n is 1, beta equal to 2, so you get lambda I power 1 minus 1, so that vanishes. So the only thing you get is the following. 1 over z e to the minus. This n comes from the fact that I have replaced lambda I by n times lambda tilde I. So this is the thing that I'm interested in, right? So here is what is an interesting observation. So if I just take out the lambda n terms and leave the other ones as they are, then what happens is that I get so observe that here I have gotten back the same density that I had before, but now for n minus 1 particles rather than n particles. So what we are really doing is that we are integrating, so this is independent of lambda 1. Okay, so there, and there will also be one c to the 2 summation log. So there were this Vandermonde term involving lambda 1, so there were, lambda n, so there were lambda n minus lambda I terms. I've just written them as log exponential of logs. Okay, so the way classical large deviation principle proof goes for lambda 1, lambda n, is that you observe that this is the n minus 1 dimensional density, and because the n minus 1 dimensional eigenvalue distribution also converge to Marchenko-Pastur distribution, you will say that this probability is just the integral of this function with respect to the Marchenko-Pastur distribution. Okay, so that's how the classical large deviation theorem is proved. Sorry, which one? Where? Yes. Obviously. Okay, so now because the term in lambda n is exponentially decaying, you essentially can replace that integral by just setting lambda tilde n equal to 4 plus delta. So this argument will show that log of delta is equal to constant times n, where this constant will come from, see, there is a partition function Zn here I am normalizing by, but for n minus 1 dimension there will be Zn minus 1, so there will be Zn minus 1 divided by Zn outside, and that will contribute a constant here. Anyway, so this is again classical from 15 years ago. This way one can prove, minus log and then delta converges to some function I delta, which is explicitly what I have written there. So if you divide by n, your I delta will be minus 4 plus delta minus twice integral of log with respect to Marchenko-Pastur distribution. But what turns out is that instead of just being happy with convergence, if you use the fact that these lambda I tildes are not only converging to Marchenko-Pastur distribution, but they are actually very rigid about the quantiles of the Marchenko-Pastur distribution, you can actually make this calculation very quantitative. So in particular, so this is something I showed a few months ago with Krishnendu Ganguly, but this was not the main interesting point. I'll come to what was that. But what I'll ask you to observe is that what it shows is that there is no subpolynomial correction. So there is a logarithmic correction. So if you look at the second order term of the large deviation, there is no subpolynomial correction. The first order term is linear, but the second order term is logarithmic. And you can do such precise calculations because you have very strong rigidity estimates. Okay, so because I'm running out of time very fast, let me quickly tell you, why we were interested in this sort of things. As I told you, I don't do random matrices. So what turns out is that such a strong asymptotics for the large deviation rate function has some interesting consequences in the last passage percolation picture. See that. Here is my square. This is 1, 1. This is n. So there is some path that attains the maximum, right? And it's a natural question to ask, what does this path look like? So this again goes back to Johansen in 2000, where he showed that if you look at the fluctuation of this path about the diagonal, so the diagonal line joining 1, 1 and nn, if you look at the fluctuation of this path around this diagonal, then the fluctuation is of the order of n to the 2/3. So it's, if you scale it, it looks like just a straight line, but if you look at it in a mesoscopic scale, you'll see that there's a fluctuation of n to the 2/3 about the diagonal. So now it's an interesting question for several reasons, which I won't go into, is to understand what happens to this path if you're looking at the condition on the large deviation event. So, it's a general question about on the large deviation theory. You condition on a large deviation event and you want to know how your statistic of interest or object of interest changes. So it's a question of interest from that perspective, that you ask what happens to this distance if I condition on the fact also that the last passage time is much larger than typical. So it turns out that if you have an estimate like this, and some more work is needed, you can show that so the reason we were interested in that result is because using it we could show that if you condition on the large deviation event, then the path actually is now restricted to a much narrower strip around the diagonal. So what was n to the 2/3 before becomes n to the half now. So that I don't have time to go into how this works, but this was a quite surprising application of this whole rigidity phenomenon in random matrices to a question that was otherwise interesting in a different world. And there are some other connections. Sorry. Yeah, for any delta, the flux. So this will be. So if you look at the deviation and you scale by n to the half, then it is a function of delta. It's a random object which is a function of delta, but the scale, the exponent does not depend on delta. Anyway, so I've run out of time, so I'll stop here, but there are some other applications where this understanding of rigidity of eigenvalues gives you some insight into questions in this last passage percolation world, which a priori did not have anything to do with the rigidity type estimates. All right, I'll stop here. Thanks.